Okay, so let's talk about relational databases. So the history here is that, which I motivated last time, I hope, is that pre-relational, if your data changed in some significant way, if you need to reorganize things in some way, your application broke. Okay, so if you changed the parent-child relationships in the hierarchical model, or if you pretty much did anything with the network or file-oriented model, your applications had to be rewritten to support that. Okay, and so early relational databases addressed this issue, and even though they were buggy and sort of slow, they required only about 5% of the code you had to write previously, and so this was an enormous win. Okay, and so this quote, sort of motivating, sort of following on what the quote I used from Kurt Monash in the previous segment, is from the original paper on databases from Ted Codd. So activities of users at terminals and most application programs should remain unaffected when the internal representation of data is changed, and even when some aspects of the external representation are changed. And so the reason I want to emphasize this is that, again, this is the key idea of relational databases, not SQL and not some of the other features that you associate with particular implementations. It's really this notion of data independence. Okay, and this was right there in the abstract in the original paper. This is the key idea. And the reason I'm hitting this so hard is that this idea is still just as important now as it was then. All right, so I want to go through some of the other key ideas that are associated with relational databases, whether or not they were in the original paper. So one key idea is that programs that manipulate tabular data exhibit this algebraic structure that we can use to reason about them and manipulate the logical model independent of any physical data representation. So what I mean here is that if you think in terms of tables and you think about the operations that tables support, you can think about what your program means and even how to optimize it, which we'll show, regardless of how the bits are actually organized on disk. And this is, incredibly powerful. Okay. So the key idea here, again, is physical data independence, and we'll talk about what logical data independence means too in the next segment. And so, the programs that you write to manipulate things no longer have to sort of manipulate files and sort of chase pointers around. You can, in this case, access it through a high-level language SQL. Although, again, it doesn't have to be SQL. The point is that you're manipulating logical structures called tables. All right, so just know the term physical data independence, and know that it means that your programs you write to manipulate data are more robust than they would be without this relational model. All right. So another key idea is that there's this algebra of tables that I mentioned, and we'll talk more about these specific operators in a bit. But at a high level, one operation on a table is to select out rows that satisfy some condition. Another is to ignore columns that you're not interested in. Another one is to, for two tables, for every record in the first table, find corresponding records in another table. Right? Select, project, and join. And there's other operations you can define as to aggregation, all sorts of set operations derived from set theory, union and difference and cross product and so on. And so these operations, if you write your expression out in terms of these operations, it's very clear what it means, and it's for software engineering purposes, it allows the database designers to focus on just implementing these operations efficiently. Okay. Now, if I had you on a classroom, what I'd ask is how many people have heard of the relational algebra, and also ask how many people have worked with databases. And typically the number of people who have worked with databases is very high, and the number of people who have heard of the relational algebra is somewhat lower. And that's one of the things I hope to fix in this course, is to equate the two. Right? If you understand databases, I want you to understand relational algebra, and vice versa, I guess, comes for free. Okay. So why do we care about this algebra? Why am I saying algebra? Well, when I'm giving a talk and describing using this slide, what I'll also ask is how many people have heard of algebraic optimization? And typically very few have, even if they're computer scientists, unless it's a room full of database people. But the thing is that you already understand what this is, right? You don't have to know databases to know what this is. This is just something you learned in high school in algebra class. Okay, so forget tables for a second. Just think about integers. Well, I've got this expression here, and I want you to evaluate this expression when I tell you z is equal to 4. Okay, so one thing you might do is just, say, 4 times 2 is 8, and 4 times 3 is 12, and so that's 20, and I add 0 and that doesn't change anything, and then I divide by 1. Fine. But if you're clever, you might notice that, well, adding 0 to any number doesn't change it at all, so I'll just ignore that altogether. Similarly, dividing any number by 1, or any integer by 1, is the same number. So I'll ignore that as well. And then if you're really clever, you might notice that there's a distributivity law here that says when I see this pattern, I can pull out the multiplication. And by applying these rules in turn, including commutativity law that allows things to be reordered, I can simplify this expression down to this. And this just says, well, now 2 plus 3 is 5. Just multiply 5 times 4 and I get 20. And I've done fewer operations. I've only done 2 operations instead of 5, and I didn't have to do division, which is potentially an expensive operator if you're thinking about a computer evaluating this. Now, do computers use this kind of symbolic reasoning when they evaluate expressions over integers? No. The answer is no. And the reason is that this kind of symbolic reasoning is much, much more expensive than just evaluating the damn thing, right? So, fine. But if the objects that you're manipulating are not small integers, but rather terabyte-sized tables, then this kind of symbolic reasoning is not only valuable, but it's absolutely critical. If you do things in the wrong order, if you do wasted work, or you do more operations than you need to over massive tables, you're dead in the water and you'll get nothing done. And so all databases, all relational databases rather, do this kind of algebraic optimization when you write a query, right? And so if you think in terms of SQL, if you're familiar with SQL, your query gets translated into a relational algebra expression in terms of selects and projects and joins, and then is manipulated according to algebraic rewrite rules, just like you learned in algebra class, and that's why the term algebra is there. And they attempt to simplify the expression. The reason I pause is simplify is perhaps not the right word, because it's not always true that the shorter the expression, the faster it is. We actually use this notion of cost-based optimization, which means we'll try lots of different kinds of equivalent expressions, assign each one of them an estimated cost, and choose the one with the lowest cost. And this is something that all relational databases are doing in one form or another. Okay. So fine. So this is the magic trick of query processing in relational databases, and this is a really, really great idea. And the reason why this works is because we understand very formally what these operations are and what they mean. Okay, and so when you relax this formal model and start allowing anybody to write any kind of code they want over the data, you lose the ability to do this kind of algebraic optimization, and you leave it up to the programmer to write the best possible algorithm. And what I'm hinting at here is, we'll talk about it more later, but when you think about writing large-scale data processing pipelines in something like MapReduce, and if you haven't heard of MapReduce, don't worry, we'll talk about it, you're leaving all the work up to the programmer to not only write the logic, but also to do the optimization. And this can impose a penalty. Okay. One final comment about this is the term algebra is not just kind of trying to connote algebra from high school. It literally is the same thing. And so when you hear the word algebra, what you should be thinking of is this notion of algebraic closure. And what I mean by that is every operation that applies to a table also returns a table. And so I can chain these operations together to always get tables. Right. Now, that's the exact same idea that's going on when you talk about operations over integers or real numbers. And you might sort of quibble and say, well, if I divide an integer by some other integer, I may get a real number, and that's true. But there's notions of multi-sorted algebras with different types involved. But the point is that this notion of closure, you can't escape the system by applying operations, is always true when you hear the term algebra. Okay. So we're not making things up. Fine. So here's some relational algebra expressions that if you squint hard enough, you can see kind of look like similar expressions over integers, except instead of addition and multiplication, we have things like joins and selects. And so what this says, I haven't shown you the query. I don't expect you to necessarily see this, but what this says is select certain values from a relation R, and here I'm going to select other values from the same relation R. That's okay. I can have two different, the relation R can appear in two different places in the same expression, no problem. And then join them together. Then select still other values from the relation R and join this one. And one way of evaluating this plan is to perform this join first and then this join second, and indicated by these parentheses, right? Another way to evaluate this expression is to perform this join first and then form this join second, indicated by the parentheses. Still another expression is to take the full cross product of all three relations, which I haven't told you what cross product is. This is actually a pretty bad one to do. If you do know what a cross product is, it generates an enormous amount of data, and you would never actually want to evaluate this plan. But you could, and it's provably equivalent to these other plans. So you know that it returns the same answer. And now all we have to do is figure out which one of these is likely to be the cheapest one, and we'll choose that one to run. And this is the kind of reasoning that all databases do internally whenever you write a query.